Okay, hello everyone. We are going to start today's webinar that is titled Tall Timber Design Under Earthquake and Fire Loads, Past, Present and Future. My name is Rafael Fernandez. I work as a research fellow in the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering. And today we're very pleased to have Dr. Solomon Tesfamarian from University of Waterloo. Before we start, I just want to mention you that as many of you already know, we have a series of webinar. It has been running for around 2 years, and we have already scheduled 3 additional webinars. The first one is in March 18 by Professor Anawad Suparsri. He will talk about the 2024 Noto Peninsula earthquake cascading impacts and lessons. Then by the end of March, we will have Dr. Sinan Akar. He will explain about the academic and professional approaches for CAT modeling. And finally, we have Dr. Sonia Giovinazzi from ENEA talking on April about a multi-criteria life cycle approach for school infrastructure improvement in the Kyrgyz Republic. Here you can see our website. In there we post the different activities and webinars that we have, and also in this same website you will be able to find the recordings of all our past webinars, and you will find also in the coming days the recording of this one. So I am very pleased to introduce Dr. Solomon Tesfamarian. He's a professor and university researcher at University of Waterloo. He has been working for more than 18 years in research and pedagogy of resilient tall timber and hybrid buildings. Specifically, his research has pushed the limits of large-scale engineering cross-laminated timber and hybrid structures in the design of high-rise building. One thing that is very important about his research is that it considers a multi-hazard environment, including aspects associated with earthquake, winds, and fire. And his research has been published through industrial reports, peer-reviewed journals, and different international conferences. So, Solomon, thank you very much for being here, and the floor is yours. You are muted.
Thank you, Rafael, Dina, for giving me this opportunity to share the work that we've been working on this tall timber. Let me share my screen. Is it okay now? All right, so I don't know what time zone you're in. It's good morning for me, good morning, and good afternoon and good evening for some of you. I'm really pleased to share the work that we've been working on tall timber, tall timber and then hybrid structures for the last 15, 16 years while I was at UBC, and something I'm continuing at University of Waterloo now. I'm a professor in the University Research Chair in the Department of Civil and Environmental Engineering. This is a great opportunity to show and then share our experience at the global audience. And this is a good invitation from Dina and Rafael. And thank you for this opportunity. This has been funding through NSERC and various funding organizations, such as Forest Innovation Investment. I had a number of students that have gone through my group that have contributed to the different aspects of this research. But today I'll try to highlight Biniam Tolderbrahan, one of my PhD students who is about to defend his PhD in 1 month, and Tonchen Han, my current PhD student who have been working on this topic for a while. So what is the motivation? The motivation is, I think, early 2000, a state-of-the-art report on CLT handbook was, I think, came to the market by FP Innovations, and then similar CLT handbook was also adopted by US, and that was the first edition was in 2013. And this CLT handbook is now also updated. The second edition is 2019. That's freely available that you'll be able to download directly from FP Innovations. So this has given us an opportunity to understand the CLT as a material, how we can use it for design concepts. I think one of Michael Green's also tall wood was sort of a groundbreaking research where using timber and hybrid structures, the concept and the idea of pushing the tall timber design was introduced. So this was a report that was published around the same time. And then also AFP Innovation came up with a technical guide for design and construction of tall wood buildings. So all these different knowledge that have been out there has given us the opportunity and then the possibility that we can push the boundary further. So this is one of those earliest building that was constructed here in Quebec City. This is a one-story concrete podium and then a 12-story CLT building. So the lateral load resisting element for this CLT building, was using CLT. And then at the time, what used to be the tallest hybrid and CLT building was constructed in UBC Vancouver campus, the student residency. This was an 18-story. So the lateral load, as you can see, were carried by the two concrete cores that are carrying the load, and the gravity system, the floor, and everything else was made out of CLT. So this used to be, at one point, the tallest timber structures. So BC Building Code adjusted upward to allow up to 12-story, and this is what came out from those existing research and the concerted research that we have done in Canada and globally. In 2019, the building height limit was pushed, and then the National Building Code also adopted it. So part of the 2020 National Building Code allows up to 12-story wood building, purely CLT, without any special consideration. 2024 now, with the knowledge and more testing and understanding, usually timber being a combustible material, fire is a critical component that has been taken into consideration. So with more understanding, more testing, and more knowledge that we have gained related to mass timber and fire-related research has given us opportunity. Also, BC has taken the lead to push the building height limit up to 18-story. This is expand the type of building that can be constructed with mass timber to include schools, shopping, and other industrial facilities, and also allowed to more exposed mass timber or fewer layers of encapsulation in those buildings. So with all this knowledge that we're gaining, more exposed mass timber and then taller mass timber structures and buildings have been constructed and used in the market. So every 5 years, there's some type of change happening. What is to come in 2029, we don't know. But there's always something exciting happening with timber. That's an area that's really emerging and then continuously growing, and then as we gain more knowledge. This is some of the information and data that I have gathered from the Council and Tall Building Urban Habitat website, and then the showed from 2015 up to 2024, and then forward, the push for tall building is increasing significantly. Like every city now is building the tallest building, and then the year after another city. And this kind of put things in perspective with the improvement of concrete strengths, how the tall concrete buildings were increasing in the 40s, 50s, and 60s. A similar trend is what we see with tall timber structures. So continuously now you'll see every city will have the tallest building, and the following year another city will come with. So most of those cities, they're not designed in high seismic zone, but this is an area that is continuously emerging, and it's an exciting time to be doing this research. So as we started, this is 14, 15 years back, we started working on these hybrid structures and timber and hybrid structures. This is one of those studies that came to our attention. This was a 12-story apartment building in New Zealand in a very high seismic zone, steel concentrically braced frame with tubular beams, and W-flange steel columns were used. But then to part of the retrofitting for this type of structures, they replaced the floors with the glulam floors. It became lighter, but then this lighter structures is good from seismic point of view. Now, when this 12-story structure became governed by the wind performance. right? So now we have two conflicting objectives that we want to reduce the mass for seismic aspect, but then reduction in that aspect is affecting the wind performance. So this is where beyond, once we start doing the timber structure and then timber and hybrid structure working on seismic, we start pushing also the boundary in terms of wind with the collaboration at when I was at UBC with Western and with one of our students. So we've been pushing the boundaries. We've done extensive wind tunnel test to understand the performance of these structures under wind load. And then as part of it also, now we have developed nonlinear wind design guidelines that were published in different journals. So this was past work that we have done, and then future work on this aspect that I'm undertaking is a point to discuss in the future. So this is some of those beyond those publications that came from our students. This is a state-of-the-art review that I wrote in 2022. You'll be able to access from public from Frontier in Built Environment. It's an open access journal. So here we were exploring multi-hazard design in terms of wind and earthquake and coupling the hazard, structural damage and loss assessment, similar to the peer framework approach is that what we have adopted. And as part of this research, we have done extensive optimization and performance evaluation of these structures, and some of those optimization work that we have implemented, I'll give as an example later in the presentation. So with this, I like to highlight a few of those buildings that we have considered and used as part of our design. So this is where initially that UBC building that you have seen, for example, the concrete core, what was used. So instead of no concrete core, the idea and the thought came, can we use CLT as a core in this type of structures? So with current design guidelines, beyond those platform type of CLT structural system, we see more and more, balloon type of structural systems. So the balloon, the CLT wall is a continuous wall system. So that balloon wall system, then part of the research that we have undertaken, we started introducing coupling beam, similar to the concept that has been extensively used in concrete. So as part of this work, now we start accounting for those coupling as part of the design. So if you want to visualize the structural system, the current design, the way even the balloon structure is being considered is what we see on the left side. Strictly, those CLT walls are uncoupled. So one innovation that we have introduced when we start pushing this boundary also is, as you can see, the hold down where the demand from that lateral road demand on the CLTs is being carried by those BRBs. So those are high capacity hold downs that we can use and we have utilized. And then the other extreme, for example, then we can have fully coupled CLT wall system. So the two wall systems are fully engaged without any type of energy dissipation. And then part of the work then we have undertaken, similar to that coupled wall system that we have seen in concrete structure, is by introducing a coupling beam. So this is a replaceable coupling beam. It's a fuse where we can allow damage to occur on those coupling beams. And then part of this performance-based design that we have developed now is to proportion the CLT wall, the size, the length of those CLT wall, to proportion this coupling beam in such a way that the hierarchy of failure as we push the structure to a higher limit, this would be the coupling beam, the first thing that would be failing. And then the hold downs will be fail-safe mechanism that's going to be failing in a hierarchical towards the end. So part of the study that done in this coupled beam system that we have considered is, coupling ratio between 20 to 50% is a sensitivity analysis that we have undertaken. And then similar type of coupling ratio were also proposed for concrete structures. So then we optimized and we came up with the design guideline to account for those coupling ratios. And then I'll show some of the results, how these structures performed under different seismic loads. So something I like to highlight, an area of interest of research for some of you could be is, quantifying damping. Damping is one of the least understood in terms of timber and timber hybrid structural system that we have. for concrete that have been extensively used historically for a long time. Damping, in situ damping has been measured, so those damping with height can be quantified. For CLT, we have only few at the time when this publication and when I wrote this paper, we had only few papers and that have reported those damping values. So with more and more CLT buildings that have been constructed, I'm hoping we get more type of this damping considered, and then we need to start accounting for the different damping mechanism. So one area of additional research and area that has to be explored, the most critical damping component in this system is the soil structure interaction. So from structural design point of view, that's an area that we don't really consider as much, but that's an important area of research and investigation that we need to sort of quantify the hysteretic damping, the viscous damping, and then damping associated with soil structure interaction is something we need to start quantifying to come up with a realistic design performance of the structure, evaluating those structures. So this is an emerging area, and that's continuously an area that we're working on. So with the coupling beam that we have seen now, so the coupling ratio is the degree of coupling provided by the coupling beam is what is defined. And you can see that the coupling beam is so the beam on the shear, and then plus that overturning moment we have at the base is what is being considered. So essentially we try to quantify and then find what is an acceptable or optimal coupling ratio as part of our design is what we have tried to consider. So most of the work that we have undertaken, we did numerical modeling in OpenSys, and detailed nonlinear modeling. We coupled the coupling beam, the BRBs, and all those elements that have been calibrated through other experimental work. We validated and then used those in our simulation modeling. So this is, for example, one of the concrete Harris and McNeese report. We can see the impact of coupling ratio on the distribution of the coupling beam shear force, right? So when we have a low coupling ratio, you can see that coupling beam distribution is more or less linear. So we can assume it's a linear distribution as we're designing it. And when we start increasing the coupling ratio, you can see now the distribution of that shear has non-linearity. So now here you can see some sort of two-step process has been utilized. So this is a case where we can use based on the mechanics we can define, and we can see the impact of those coupling ratio on the overall response of those coupling beam shear forces. And then further extensive work that we have done on this one is to use optimization and then find, without any type of assumption, how that distribution should be. By giving it a lower and upper bound, we try to optimize and then find what is the optimal distribution that we need to get for this coupling ratio. This is looking at those structures, impact of coupling ratio on the, say, for example, the pushover analysis that we see on the left side. And then the middle part, the drift, and you can see the hierarchy of failure that we have obtained. So the impact of the coupling ratio can be observed. At the same time, the hierarchy of failure, where we can see the middle part where the hold downs are failing or going to nonlinear phase at a very high drift ratios, but at a drift ratio of around 0.5, you can see in a hierarchical way the different beams are going to the nonlinear phase. So this is sort of that performance-based, capacity-based design process that we have introduced. We're trying to control the hierarchy of failure between those coupling beam, the hold down. As I said, the hold down will be our final safe, fail-safe mechanism to dissipate the energy, because that's the only non-redundant system that we have. But with the coupling beams, there's a redundancy also in those type of systems. So similar to that concrete relationship that I have shown, also the impact of those coupling ratio, you can see from these figures, when the coupling ratio is 10%, more or less linear is a good representation. And when coupling ratio is 50, more that bilinear step type of relationship is what we need to consider. So this shows us sensitivity and an impact of those coupling ratio on the overall shear force distribution. This also shows that the axial shear force and moment between the different coupling. This is for coupling ratio of 30%. And the part of the work that then we have done in this case is the case study was for Vancouver, and Vancouver is in a very high seismic zone. It's one of the seismic seismic source that we have here is the Cascadian subduction zone. We are expecting a magnitude 9 earthquake, that has recurrence of over 300 years period. That's something we are expecting in that region. So as part of this analysis, then we have accounted for different seismicity. We use the fully probabilistic seismic hazard model to deaggregate the different source of earthquake and then accordingly select ground motions that are representative for the specific site. For example, the Cascadian earthquake, Tohoku earthquake type of, or the Chilean earthquake that have a long duration earthquake is more representative. So then site-specific ground motions are selected from the appropriate sources for the different earthquakes. Here is an example where at the bottom you see is the input ground motion, and then the top floors for the drift and acceleration. You can see at different floor levels for that 20-story structure that we have looked at, the response at the different story level. And then on the far right, then you see also the response of the hold downs, and you see the impact of the coupling ratio. When the coupling ratio is, say, 10%, the coupling beam is going to nonlinearity more, and then the shear demand is less. Whereas when we have the coupling ratio is 50, so then the force, our design force will be higher, and then the displacement will be reduced. So that's sort of what we need to do to find the right balance between that excessive deformation that we have and then the force distribution that we need to undertake. So this also shows us the response of the hold downs from this coupling beam. So this is the response of the coupling beam we have on the right side, and then this shows us the response of the hold downs from those seismic loads. Impact of the coupling ratio, as you can see, if the coupling ratio for the 10% is going through excessive deformation, and the demand we have on the hold downs also is reflected, and similarly for coupling ratio 30 and 50 and so forth. So then the design is trying to sort of finding the right balance between proportioning the coupling beam and the hold down is what we are interested. And then we've done incremental dynamic analysis, and then we pushed it all the way to collapse. And then from here, we can see the collapse fragility for the different coupling ratio. So this is just one system to highlight and how we have done that performance-based design for that system. So for the most part, and as we're investigating this type of structures, the moment resisting frame that you see here on this figure, for example, is often neglected. So we just account only for the shear wall without accounting for those gravity system that we have. So those gravity system now, if we change it into a moment resting frame, then how can we do our design is part of the work that we have done, Biniam has carried out and funded by that Forest Innovation Investment. So with this type of analysis and proportioning the design entails finding the right balance between the shear wall and then the moment resting frame. Right. So then we need to proportion it, like I say, for example, the shear wall will carry 60%, the moment frame will carry 40%, and then so forth, and then go through this design process. So this shows us when we have only a CLT, we'll have rocking and then bending type of deformation. With the moment frame, we have this shear deformation. Now we have a combination of the two that has unique deformation patterns that will affect the response and the structural performance of these systems. So given that triangular load, for example, that has been applied, you can see how the forces are distributed between the moment resting frame and the shear wall, and then the overall response is reflected on the right side. So again, we developed a performance-based design guideline to understand the different steps and design process for this type of structural system. And then here we have utilized OpenSys also for modeling. As we increase, we use computational intensive ground motion, a lot of nonlinearity and so forth. So OpenSys was a useful tool that we have used. And then we developed also in-house ground selection tool and also seismic hazard model with related to the the 2020 National Building Code of Canada. Here again, we can see the deaggregation of different hazard ground motions that we have selected. And then based on this now, we carried out the performance assessment to evaluate. So for the design level earthquake in the Canadian system for 2% in 50 years, our objective is collapse prevention, and that maximum interstory drift is about 2.5%. You can see how the structures are performing under that intensity level. So once we have now understood the structural system modeling and then how we need to analyze our structure, we've done also a number of different optimization in terms of our design. So beyond now using those coupling beam and beyond using those shear walls, here we have introduced outrigger into our system. So with outrigger, now we are increasing the stiffness without increasing the strength of the system. So as part of the design of this outrigger is to find, say, for example, if we have only one outrigger, what will be the optimal location of that one outrigger? If we have two outriggers, our interest in terms of design is to find what is the optimal location of those two outriggers. Was part of the design optimization problem that we have carried out. This was done by Shourav Das. And then here, interesting damper was utilized. Here, shape memory array-based damper was utilized. So that has a recentering capability. So now with post-disaster, we're exploring for resiliency and less damage in terms of our performance. This type of SMA type of dampers will have a recentering capability. So that was part of the optimization that we have undertaken. And this simulation was done in MATLAB platform, and that was the publication that came from that exercise. So part of that SMA, so that nonlinear flagship deformation pattern that we have was converted into an equivalent linear system as part of that modeling process. And then our objective is to minimize the interstory drift ratio and also minimize acceleration. So these are the two objective functions that we are considering, right? So the moment we start reducing the drift, acceleration will increase. The moment we start reducing acceleration, the drift will increase. So now we have two objective functions. So as part of this objective function, now we need to start finding the Pareto front to decide what is the best way of modeling this structure. So these are the different constraints that were introduced. So in this case, Shourav used some multi-objective optimization using genetic algorithm. So with by coding the different functions, then we can start finding what is the optimal distribution. So we can see from the optimal distribution how introducing the outrigger contributed to the overall response. So here you can see the location of those outriggers. And then this is the only one outrigger system when you have two outrigger systems. And then at the same time, here is the Pareto front that we have obtained. So the Pareto front is where the optimal, we cannot improve the drift level without compromising acceleration, and we cannot improve acceleration without affecting the drift level. Now, as a designer, now you have the option, what is the acceptable level of acceleration, maximum acceleration for your system. Then you can go and find what will be the maximum drift that you'll be expecting. Or you may have a drift control requirement. Then for that, you can see what type of acceleration that you'll be getting. So this type of scenarios, now we can start introducing supplemental damping and other techniques to mitigate and then find what is the acceptable performance for this structure. So I'm just giving you a quick highlight before we go to the fire part of the work that we have done. This is Rafael LaGuardia, Paolo Frankin, the work that we have done. So for this, again, timber type of structural system that we have, here we have used glulam columns. But what interesting part of this study is using the BRB as a brace system that you see here. And most interesting about this work is we have used instead of using genetic algorithm where we don't have guarantee of optimality, here we have used derivative-free optimization. So with the derivative-free optimization, now we can, one example that we have Raffaele used is generalized pattern search. So this one now there's a guarantee of optimality. We know we have obtained the absolute optimal point for the simulation that we are undertaking. So then we different optimizations were and search algorithm were also utilized within this approach. And then most importantly, this design was sort of carried out as a risk framework. So instead of the drift or acceleration performance level, that integrated with the site-specific hazard level was the risk was closed form solution for the risk was obtained. So then part of the objective for our optimization is minimizing that risk. So with this now we can see the different configurations of those outrigger, those brace system and sizes that we needed to find. And then this is part of that work that Raffaele did to optimize. So with this type of simulation, he used SAP as a sort of as a structural analysis software. But then the challenge with this one now is we have to continuously. So if you relate it to MATLAB as a sort of as a platform, so continuously we need to interrogate and interact with the SAP software. So alternatively, these days, the surrogate model also is being used. So with surrogate model, now we can do the design of experiment, identify some of the key sampling points that we are interested in. And then for those sampling points, then we can create sort of a function to represent the overall response of our structure. And then our optimization now is done on that surrogate function. So here, there's a difference here, the design of experiment sampling used, and this is a surrogate model that has been developed, and different type of method can be used, and we have utilized in our research. And again, this is part of the work Shourav did. Here, we're using a system, a brace system that has a viscous damping and self-centering capability and a steel structure. So for this steel structure, robust design optimization was utilized. So as part of the ground motion uncertainty and response that we have, so there is uncertainty on the mean and standard deviation. So with the robust design optimization, instead of now controlling only the mean, so we're trying to sort of minimize the mean, and then the dispersion over the mean is part of the optimization. So then we need to proportion it as a multi-objective optimization problem, and then carry out. So here, the performance level that we are interested in were introduced as a constraint. So, but the response is what has been used as part of the objective function. So we have multiple and different way of dealing with the multi-objective optimization problem. In this case, the surrogate model Shourav used is a wavelet neural network-based optimization. So then once we have developed our surrogate model, so based on the surrogate model, that was developed both for the mean and standard deviation in a multi-objective optimization framework. Now we can minimize the two aspects. So here are the different values that we used. And here we can see how the Pareto front and what type of Pareto front that we have obtained, with the different type of design configuration, with self-centering, viscous damping, only with self-centering, only with viscous damping, and so forth. So if we start changing the type of brace that we have, this was sort of a sensitivity analysis that we have undertaken. So we have also explored in the interest of time, I will not have to go through those details. We have also explored high-dimensional multi-objective optimization problem for this type of structural system. We use the deep neural network and then other advanced machine learning techniques to come up with the surrogate model. And then based on that, we have optimized it and then obtained for this structure. This under review actually is accepted, is published. You can find it online. So then well, maybe 3 years ago, when I was sort of in the process of moving to Waterloo, I realized we have a very good fire facility. And then I have decided and thought maybe I need to sort of align and start pushing beyond that wind and earthquake aspect of the timber structure to bring fire in terms of the research component. So with that, this is some of the highlights, the testing facility that we have in the University of Waterloo Fire Group. So there are a lot of testing facilities. We have a large testing chamber here that we can utilize a different type of structural system for testing. So it has 6 wind tunnels to represent in situ condition for outdoor exposure. And so we have a controlled environment for testing. So these are sort of what gave me the motivation and the idea of bringing multi-hazard fire into the timber. And then timber and fire has always been also the governing criteria for the tall timber structure. So bringing that timber sort of in a performance-based framework was a logical extension of the research that have been undertaking. So one of the first thing that we have undertaken with Tongchen as we were exploring fuel load is, for example, for office occupancy, for different occupancies is a given information. But now when you have timber becomes a tricky component. Timber does contribute also to the fuel load. And then once it goes through certain charring, the timber will start protecting the fire, further burning from the fire component. But then that initial fuel load that has to be added into the room load that we haven't considered before is part of the exercise that we have undertaken. So this for Eurocode, different codes, for example, for the type of occupancy, the average fire density is provided. But when we have timber, how can we deal with it? So with this type of research, then this is some of the published work that was carried out by NRC and the NIST group, and that's publicly available information. So now we took one example that has a rough opening of 3.6 by 2 meter wide with exposed structural system. So we took one of these experimental tests by that NRC and NIST report. And then from here, we try to reproduce and understand if we can capture. So at the end, we start dealing with fire. We need to have a good model and understanding on the fire temperature relationship. So what type of fire temperature load we need to apply so that we can do the thermomechanical analysis and start investigating the performance of the structure. So this is one of those experiments from the NIST. And here the fire load that was introduced for that NIST experiment is shown in this figure. And then from here, you can see also how the different burning at different time steps were observed from that experiment. So now by taking this experimental test, now we start modeling it using different softwares. So one of the challenge and the problem of timber also, you can see here, we have the fire growth. And then once we reach flash over, we have a decay, but then often the timber, glulam and CLT and so forth, there's a potential for delamination. Now that's more fuel load is added, and then that's gonna peak and then continue through this phase. So as part of our modeling that we have undertaken now, we did not account for this delamination and this type of failures. So these days, if there is a proper gluing is used and so forth, those type of things can be eliminated, but this is not what we have considered in our analysis. In this case, we have used the Ozone software, the publicly free available software. So taking the timber as a fire load and then plus the fire load that was reported. And so we use that information, and then from there by modeling that structural configuration that was shown in that experimental test using Ozone, what we are interested is to come up with a realistic time temperature relationship. So what you see on the left side is heat release rate, what was measured from those experimental tests. And then the calculated heat release rate is what you see on the right. On the right part, the The black line is if you use the European parametric curve, this is the time-temperature relationship that you'll be getting. And if you do the ISO standard test, you can see just as a benchmark, the blue line is what you have. And the gray lines that you see on the right side is the time-temperature relationship that were obtained from the experimental test. And then the red is using the modeling, what we have obtained without any calibration and further modification. So this is now we have compared to that European parametric equation, we have more realistic fire temperature relationship that we were able to use. So now if you have a structure like this, and then how can we model it? What are the challenges that we have when we start modeling this under fire load? So there's a challenge in terms of computational efficiency. Here we have used Abaqus, for example, for the fire modeling. But then when you start modeling the different column, the shear walls and the connection and so forth, it's a very computational intensive to do that thermomechanical analysis on this type of structures. So as part of this one, Tongchen took some published literature from Guernes and the column test. And then from here, he developed a simplified modeling technique where instead of using a full-fledged 3D brick element, converted it to equivalent beam element through by finding this equivalent section temperature that will give us the same strength capacity as a full-fledged element. So this type of approximation and transformation, now that what seems to be complex 15, 20-story structural system, we can simplify it to a simple beam element as we're modeling those columns for those type of structural systems. So we took those experimental tests. Here, what we see on the left is a full-fledged brick element with all the charring reflected. And what we see on the right is an equivalent beam section that we can use for this type of element. So we can see the vertical displacement time relationship with a simplified approach, and then detailed 3D brick element. We have a very good approximation on this type of structural system. And then as this paper was under review, also a question came, we have implemented it for columns. Is it applicable to other type of structural systems? So then we extended, Tongchen extended that study to apply it for beam element. And then here is what was reported in that experiment. And they can see here deflection time relationship for the beam element also. So this shows the modeling approach that we have considered is versatile, can be used for different structural elements. So what seems to be a very complex 3D brick element, detailed finite element mesh element is now converted into simple beam element for the beam and column sections. Further modeling was undertaken on the connection system that we have. So with this connection system, one of the connection system that we have considered is bolted moment resisting system. So with a bolted moment resisting system, now you can see what type of testing. This was a testing that was done at Tongji University. So we took that paper, that testing configuration. This is how the testing was set up. And then again, initially we used high fidelity modeling for the beam, again, similar to discretizing the steel element, the beam element, and all those structural systems. And then this becomes a very computationally intensive exercise. So as part of this one, also we developed simplified spring model, similar to what used in steel and other structural element. Now we can convert this complex model into a simplified spring model, and then now we can increase the efficiency and speed in terms of our computational effort. So this is the structural system that was reported from that study. These are the different properties that were reported from those studies. So taking these properties, here you can see the full discretization modeling of the glulam beam with the steel slit and then bolt connection. The material properties and the modeling used for these elements are reflected here. From this high fidelity model, we can see the moment rotation from the high fidelity model and the experimental test. that were reported. Again, we have a very good approximation and handle on the modeling aspect for this structure. This is some of those European modeling information on the conductivity, specific heat and density, how it affects and changes with the temperature as part of the constitutive modeling of those different elements. Similar for the bolt and then the steel element. Also, the specific heat and the conductivity as a function of temperature were introduced. So now, by doing this type of modeling, now here also the structural analysis of timber, how the timber changes with the temperature, the reduction factor in terms of strength and more or less of elasticity, and then reduction factor in terms of steel strength. Also, the function of temperature is taken from the European code. So using this information, now we can see the rotation time relationship, how we have obtained a good approximation on the response. So this shows us the overall response as we're subjected to high temperature and deflection for the specific column that we're considering. So here, the spring for each bolt that we have, they are connected in series, and then each represents sort of the Johansson's failure theory that were reported in the Canadian code and the Euro code. So then these are for each bolt, whichever criteria will govern the failure, and then each bolt are represented in this approximation. And then based on the mechanics of those system, now we can get the shear deformation for the tension spring, shear spring, compression spring, and rotational spring based on the high fidelity and simplified model is what you see from this analysis. Now from this approximation, now we can see the high fidelity obtains and gets a good approximation on the overall rotation time rotation relationship up to like 30 minutes. Also, the low fidelity simplified approach has a good approximation, but then after that, sort of it gets through excessive deformation without increasing in time. So this sort of gives us a multi-fidelity modeling approach and extension of the work that we are undertaking. So now with the simplified approach, we can have more simulation, we can propagate more uncertainties with high fidelity modeling that we have. Now we have computational intensive, we can do only less number of simulation. Now we can combine the two in a multi-fidelity modeling, and that's the extension of work Tongchen has already done. Just to put this in perspective in terms of what we have done, our analysis, all those beam approximation, connection approximation, everything else that we have, and then with the modeling validation, time-temperature relationship that we have seen. So now in a sort of organic way, we brought in terms of the earthquake and wind performance-based design that we have undertaken, fire performance-based design is currently what we're working on. So we're developing a fully probabilistic performance-based design for fire that accounts different type of fidelity in terms of model resolution as part of the analysis that we have. Here again, the same type of structural system that we have considered in the past was utilized. You can see the red dots are where the columns are reflected and the shear wall is in the middle. So you can see the compartment for this building are also reflected. And this shows the elevation on the X and Y direction of that structural system. Here you have a 3D representation of the overall structural system that we have considered. So interestingly, as part of the performance-based design, now fire scenarios has to be undertaken. So fire is a probabilistic sense. We don't know at what floor, which locations the fire will initiate. So this is where now we can start considering the location of the fire in a probabilistic sense, and then we can start aggregating all those information. So for this case, for example, here on the 3rd floor, the fire on this exterior side was introduced, and then based on the previous ozone model that we have seen, different type of exposure were considered, where now we have the natural fire based on the loading, the fire load for the room that we have considered, and also if we start having exposed timber for that floor level, now we can see exposure 2 is what has been considered And then the same type of modeling that we have seen in the previous presentation was considered. Three protection strategies were considered here. So this is also the opportunity we have now is we can start going through a performance-based design. Instead of a prescriptive design, we can start considering in what-if scenarios. So like once we have this refined model is available for us, here, for example, no fire protection in structural component. Second one is protecting it with the 15.9 millimeter gypsum board. Often this gives us about like 30 minutes delay time in terms of fire initiation. And then scenario 3 could be, for example, and instead of all columns, we can strategically start retrofitting certain type of structures. So this shows those columns that were investigated. And then given the type of floor system that we have, and that ozone software, we can see now the fire load with the CLT exposed and not exposed as part of these two scenarios. And the temperature relationship is reflected on the right side. So from here now we can see. So this is without any type of protection, and the fire happened on that third floor. You can see now those local buckling and then failure of those columns. So with this type of scenario and then understanding, now we have an opportunity to come and retrofit those columns, right? Then we can start, here is the close-up view of the load displacement and the failure of those columns from this high fidelity model that we have undertaken. Now, if we retrofit all those columns, you can see they all look great because the value that we have here is very small. So now we can see with those retrofitting and that the fire initiated at that level, there is no damage. That's protection. We have enough protection for that gypsum board that we have introduced. And then again, optimize protection. Then we can start creating scenarios. Where is the optimal location to do this retrofitting as part of the exposure and the structural system that we are undertaking. So this sort of shows us, how we have extended the knowledge that we have gained in terms of timber design, brought the wind component to it. Now we are extending it to fire, where we can start integrating in a performance-based framework. The feature is in the multi-hazard. We're trying to pull all this information together so that we can have more safer, reliable, and controlled failure and design process. Thank you for your time and attending.
Thank you very much, Solomon. It was very interesting to see all the work that you have done around this. It's truly impressive. We have some questions. So let's start with the first one from Guillermo Gonzalez. Guillermo, are you connected? Would you like to expand on your question?
Yes, can you hear me?
Yes, please. Go ahead.
Okay. Yeah, I would like to know when you show the shear walls at the bottom, there will be high forces there. And I just want to know how you manage to transfer that force through the CLT down to the fall downs. I'm just curious.
Yeah, Guillermo, I think that's the next phase, Guillermo, that we are undertaking. So what we have done is they're mostly on the simulation aspect. So we have up to with optimization, we have managed to reduce it to 2000. So like this summer, for example, we'll be taking doing a BRB hold down test up to like 350, 400 kilonewton. So now that's part of the optimization and then practical implementation that we need to start thinking about. So instead of maybe one BRBs, we can start distributing and then use multiple BRBs and so forth. I agree, like transferring that 3,000, 4,000 kilonewton will be challenging with the CLT system that we have.
Thank you very much.
Thank you.
Yeah. Now let's go to the next question. It is posted by Shmuel. I don't know, Shmuel, if you are here. I see that you have two questions, so maybe you can take this opportunity to answer both, to ask both.
Shmuel, you gonna ask your question or? I mean, so what would be the role of government in the effective tall timber design? I think, in Canada, for example, we have a very strong and stringent design criteria that has been introduced. So maybe the government can give incentive for giving the designers opportunity to adopt those innovative type of systems. But then the regulation, the design guidelines, and those they need to have a stringent design control. So we have a very good check and balance in terms of innovative design, and then the code at different level, the code from provincial to national level, the code, the design to have sort of those check and balances, right? So the government will have a role in terms of giving incentive for the designers, the builders, and so forth. But at the same time, we have independent body of the design and code committee that will oversee this type of future directions.
Thank you, Solomon. And the next question from Ismael was, how, according to you, we can protect from fires and earthquakes on buildings, including timber elements in areas with poor and low socioeconomic population?
Yeah, so that's if it is exposed to steel dowel, I mean, steel is very conductive material. So under fire, then the best thing is to sort of encapsulate and then protect those steel from that exposed system. And then the problem also with fire is the potential to charring of the timber, shrinkage, and so forth. So we need to find the right balance. So that connection has to be encapsulated and protected properly, because that will be sort of where our fuse that will be dissipating and contributing to overall dissipation of the system that we have.
Thank you, Solomon. Let's go now to Fritz's question. Let me see if Fritz wants to maybe make his question. Fritz, do you want to expand?
Okay, hello.
Hi, yeah, we can hear you.
Yeah, Prof. Solomon, thank you for your great presentation. I just a small question, I think, yeah. When we talk about steel or concrete, maybe we can make sure the consistent of the strength and the properties of the material. So how we can make sure the timber consistent in the strength and other properties?
Yeah, I mean, I agree. I mean, timber by itself is a very heterogeneous, but then with the engineered timber that we're using, like glulam and CLT, now it's a composite system that we are creating. So if we do those testing, then we have now consistent strengths and other properties is sort of provided. So with the engineered design and product that we have, we have that opportunity to have those consistency. But then wood by itself is naturally growing and then very different material, so we have no control on it. But as an engineered system that we have with CLT and glulam and so forth, now as a composite system, we can have a better quality control in terms of the overall performance of that system.
Okay, thank you very much, Prof. Solomon.
Thank you, Solomon. The next question is from Omar Flores. Omar, do you want to make your question? I think that maybe Omar is not available, but in any case, what about the general durability of such kind of buildings in the long term?
Yeah, I mean, moisture and all other component. I'm not a building science person, but Omar, I agree. That's the key component, even if you see that if innovation guide and so forth, those durability and performance and long-term factors have been considered, and that's part of the overall design process. So I kind of focus more on the structural integrity, but that building science aspect and that durability issue is, again, a big part of the design process that has to be considered.
And our last question is from Nadia. I think that Nadia is also here. Nadia, would you like to expand on your question?
Of course. Thank you very much. It was a great talk. My question is, I'm a fire engineer and I look at it from a fire engineering perspective, and I see the speed of number of tall buildings, timber buildings that we are building in different parts of the world. And as a fire engineer, I think we still have a lot to learn and catch up. But I just wanted to hear from you from the structure side, how comfortable and confident you are with this speed of build environment.
I think that's a good question, Nadia. We get to see like more and more fire tests for those timber structures, and as the fire with 1 hour, 2 hour fire exposure and so forth, timber, if there's extra layer that we are always providing, after certain charring, the interior part of that timber is still intact. So we've seen extensive tests on this type of structural system that have performed well as after the fire. So in an overall fire safety point of view, yes, there has to be sort of fire safety engineers, and like you have to optimize and you have sprinkler and other defense mechanism also you need to introduce. But from the testing that we have seen, those fire have performed well after even extended fire exposure. Some of the tests that I have attended here, Canadian Wood Council, here in Ottawa, where after extensive 2 hours, 3 hours exposure without any firefighters intervening, the fire extinguishes and the structural system is still intact and it can still carry more load.
Thank you very much. I think one observation that we had, and it's still a very hot topic in fire community, is we have too much reliance on the fire test, and our fire test is over 100 years old, still working for basically designed for non-combustible material, and still works quite well in the build environment, and it gives us enough redundancy, enough safety when we are designing a building. But still a lot of debate is going on if it is an appropriate test for timber. So probably in coming years, we will see some suggestions, some new proposals for the new way of testing, which is the same for for example, external walls, that we still don't understand how to test them because none of them shows the real fire scenario. And I think the challenge for me still stays for timber, that we really need to find the best way that we can test it first and then rely on that test for the future. But I really appreciate that you also shared your opinion on that.
Sure.
Thank you.
Thank you very much, Nadia. I think that we don't have more questions. So nothing else but to thank you, Solomon, for this very interesting presentation. Thank you to all our audience. And we look forward to keep working together to keep this interaction. And we will, as I mentioned at the beginning, upload this into our website, so you can also go and see again and share this with your colleagues. Thank you very much, Solomon.
Thank you, and thank you, everyone.
And thank you, everyone.